So good morning, everyone. So this is session 11, conceptual models, meta models, and taxonomies. We have three very interesting papers. I'm very happy that I was chosen to chair this session. And we'll start with the first paper, towards interoperable metamodeling platforms, the case of bridging ADOX and EMF. And this will be presented by Kostas Anagnostos.
Yeah. Okay, thank you. So welcome to our presentation where we will present the results of our work towards interoperable metamodeling platforms, the case of bridging ADOX and EMF. So my name is Costa, and together in this work was Dominik Borg and Manuel Wimmer from JKU Linz, who cannot be here today. So starting off with the introduction and the motivation of our work. So in order to understand metamodeling platforms, we first have to define some concepts. So when we talk about modeling languages, those are ubiquitous information systems, meaning that they are very popular among developers out there. And they're very powerful in the extent that we can create very easily very powerful software with them. And they are composed of three different artifacts. So one is the abstract syntax, which is the so-called metamodel, which I will come to in a minute. Then the concrete syntax, which is the visualization of the models, and the semantics, which carries the meaning of the actual models. And then there's metamodeling platforms. So those are usually software platforms that are used to build those languages in a very intuitive way. And through that, we can define the abstract syntax, which is the metamodel. And additionally, they enable also the generation of language editors and tools that we can use together with these environments. So when we talk about metamodeling, I think most are familiar. So the central entity is the model, which is there in the M1 layer. And a model is usually an abstraction of a real-world scenario. And how do we define a model, or how do we define what elements a model can consist of? So this is done by the metamodel, which the model conforms to. So we can climb this ladder up, and the definition of the metamodel would be the meta-metamodel, and so on. So this is in the context of metamodeling. And now we introduce the two environments that were used for this work. So on the one hand, we have ADOX, and on the other hand, we have the Eclipse modeling framework. So they have similarities in some extent, but are also different in some extent. So ADOX comes from the academia side, and it comes with its own and very stable dev environment. It has advanced graphical features, what it is known for, and it is open use if you have the adequate license. Eclipse modeling framework, on the other hand, has very strong ties to Java, so making it very familiar for Java developers. It supports lots of plugins, and it is open source, so both the meta model and the platform itself, because it's based on Eclipse, it is open source and therefore has a great open source community behind it. So why we introduced the model layers, the meta model layers, is that we can easily also transpose this into those platforms. So when we look at the top, we have the meta model layer, which for ADOX is developed by the ADOX developers, and for EMF by the EMF developers. And going one level down on the meta model layer, which this work will focus on, this is the user. The user can specify the meta models on this level and create meta models out of that. And for ADOX, we have a special case as opposed to Eclipse. So in Eclipse, we only have a user-specific meta model, and in ADOX, we have an abstract ADOX meta model, which we have to inherit from in order to generate the user-specified meta model. And those can be exported in XMI for EMF and in ALL, ABL, or XML for ADOX respectively, which will be important for the later steps. So now imagine that there's two developers that want to develop on a meta model, and they usually use only one platform. So we usually have this lock-in of a user, so whenever he starts to use a certain environment, he will usually not switch to it, or because there's teams that are adapted to a certain to a certain environment, can use the best tool for the jobs and so ever. And what we want to achieve is we want to bridge those, so we want to connect the two so that we can use them interoperable, so that we can use one meta model in the other platform and vice versa. And in order to do this, we propose to create bridges, or to be precise, to unidirectional bridges from either direction to the other, in which we transform one source meta model to a target meta model of the opposite environment. And with this, we can close the loop and the gap, and therefore create interoperability. Coming to the metamodeling platforms themselves, so just a brief introduction, A2XX. So this is the metamodeling environment. So if you recall, this was on the M2 layer. A2XX offers a tree-based editor to create those metamodels, and EMF offers a graphical UML-like syntax to create metamodels. So it's a bit more intuitive and easier, especially for UML developers, to create metamodels in this platform. And funny enough, on the model layer, so this is one layer below, it's the other way around. So A2XX is very known for its graphical features, in which we can create models from. And in EMF, we have, at least out of the box, this tree-based structure, where we can create models from. But in EMF, there's also a lot of plugins that could support graphical features or graphical syntax if we would install them. And these are the meta models of the two platforms, so of EMF and A2XX respectively. And there's a lot of information here, so we will not go too deep into it, but it's just to show that why we do need these bridges is that they are very different in nature. So every meta model has different features that the other environment maybe does not have. And that is why we do need a distinct pattern in order to transform those. So for the next step, we compared the meta model elements, so on the M3 level, and put them here in this chart. And with this, actually, we were able to define the differences between, or the similarities between the two meta models. And from that, we can derive the rules later to create the meta models. And a lot of them are what I would call trivial. So for example, when we look at core modeling concepts of class, there exists a class object in A2XX and a class object in eCore, which is the meta model of EMF. So this mapping would be trivial. So we can map one class to an E-class and so on. And also for attributes, there's primitive data types that we can map from one way to the other. And this I would call trivial mappings, but we wanted to focus here on distinct differences between the two environments. So for one, we have the predefined root element, which in A2XX does not exist, but in EMF we do need a predefined root element out of which we can create all the other elements from. And then the composition feature, this is not natively supported by A2XX, at least it's only visual. And in EMF, we have a distinct composition feature, so meaning whenever I create composed instances, there needs to be a container object available and so on. And probably the most notable difference between the two environments is the inheritance multiplicity. So in A2XX, a class can only inherit from one other class, while in eCore, a class can inherit from multiple classes. So coming to the transformation bridges, so what did we do in order to map the elements from one platform to the other? So this is a brief overview of the whole procedure. And for in the middle, the mapping-based transformation, we use the rules we derive from this table. So, and they are composed of the both meta models, which you can see on the top. And when we go one layer below, so on the meta model layer, how do we transform one meta model from one source environment to the other? So when we go for A2XX, we can export this user-created meta model via XML. And then we read it, so everything in the middle is our transformation procedure. We read it in via JAX-B, and then use the EMF API to create the EMF elements in a Java internal structure. And from that, we can export it actually to an eCore file. and this we can then import into the EMF environment. And for the other way around, we can use also use the same metamodel file from eco with the same ending and import it to EMF. And then we use the 802.xx ALL API, and this is also a Java-based representation of the metamodel. And we have to use another public service made available by the 802.xx developers, which is the ALL to ABL service, because when we want to import a metamodel into 802.xx, we can only do this by providing an ABL file. And this is the only service that can transform this into an ABL file. And then we can import it into the 802.xx environment. So the two distinct features that I just want to briefly mention here in the transformation that required kind of a lot of work was the composition replication. So when we look, a database object can consist of multiple table objects. So in EMF, whenever we create or want to create a table element, there needs to be an instance of database first. Or the other way, if we delete an instance of database, all other elements of table are cascade deleted as well. So we had to replicate this behavior in 802.xx because it's not natively supported. So what we did is we used AdoScript for this. And AdoScript is just a scripting language of 802.xx in which we can manipulate the model elements during runtime. And what we basically did is hook into the two events, so the after create modeling node and the before delete instance. And there we just perform our code. So we check if there is a container instance available, or if we delete a container instance, we cascade delete all other elements as well. And for the multi-inheritance mapping, there were multiple approaches possible to mitigate them. So we chose for the adapted expansion pattern. And why this is important is because we only have single inheritance in 802.xx, but we can have multiple inheritance in EMF. So the left meta model would be a valid EMF meta model, where the class E inherits from both B and C. And class C has also an incoming relationship from X, which would implicitly also be valid for X to E, since E inherits from C. And what we did with this adapted expansion pattern is that we made the class E in 802.xx only inherit from one class, so this was eagerly chosen. And then we copied the attribute C into E. So this way we preserve the semantic information. And for the incoming relationships, we created a new relationship from X to deconstruct. And deconstruct is really just the superclass of every other 802.xx class, so it can kind of be compared to object in Java. And we defined a constraint on this relationship. And we had the benefit here of doing it this instead of drawing individual relationships to either node or to either class, that we avoid a lot of redundancy. So we only need to define this relationship once and just define the constraint on it. And this is an illustrative scenario. So this is from a fleet management example. And these are the different elements. So on the left is the 802.xx source meta model, and on the right, the EMF target meta model. And we map the different elements in this way. So it is a lot, but what's important here maybe noting is that in 802.xx, relationships are standalone objects, while in EMF, they are incorporated into the source class of where the relationship originates from. So this is depicted here. But in general, the classes are copied, the attributes are copied, and so forth. And for the other way, which is the more interesting one, is that we have multiple inheritance in EMF, but single inheritance in 802.xx. So when we look at the hovercraft class, it inherits from both land vehicle and sea vehicle. And we made it inherit in 802.xx only from land vehicle. We copied the old attributes that were only present in sea vehicle also in there. And we created this relationship C vehicles, which goes to deconstruct, and where this, this constraint that I talked about is defined on. So coming to the evaluation of our approach. So our overall objective was to enable interoperability for cross-platform development. And out of that, 3 research questions arose. So for one, we wanted to check the meta-model validity. So if our transformation produces valid meta-model files in the target meta-modeling platform. And we could do this by actually just validating the import capability. So if we can import the meta-model without errors into the other environment, we could actually show that they're valid. Then the meta-model expressivity. So there we gathered different metrics from the source and transformed meta-model file, like class, attribute, and relationship count. And we used this to verify the different behaviors. So for example, if I expect like the same amount of classes in before and after, I can actually verify it through this. And the model processing equivalence, so this is more of a question, how do the 2 platforms behave? So do they behave similarly? And this is especially, so here we tested those features like multiple inheritance, for example. So does this behave same in one environment as it does in the other? And for the experiment, we used 78 meta models of ADOXX and EMF combined with different metrics. So we just wanted to have a variety of different meta models there with different metrics. And just to give like a more general picture and make general conclusions about our approach. And for the first research question, the meta-model validity, we imported the meta-model files into the target platform. And for the direction from ADOXX to EMF, we could actually verify for 100% of the cases of the test set that there was no errors. So we could indeed import them without any errors into the other environment. For the other one, we could also do that for almost every meta model except for one. So there was one meta model which produced internally a very, very large string. And this string does not fit into the ADOXX data type string because it's limited to 3,700 characters. So this is really a limitation of the ADOXX platform. But there is a possible solution to this problem because we can use external loading. So we could save the values in an external file and just load them during runtime and therefore mitigate this problem. So for this, we concluded that we were able to show meta-model validity. Then for the meta-model expressivity, so this is where we gathered the different metrics from source and transformed meta-model files. And here is just an excerpt of a few meta-models. And on the left, we have the ADOXX metric. On the right, we have the EMF metric. And here we can see, for example, if we expect certain values, so we know there is a one-to-one mapping of classes, we can actually validate it here. So this number has to be equal. Or if we expect to have more relationships in the other environment, for example, like here, then we can also validate that this number is also higher. And for every meta model in every direction, we could also verify this. And for the very last, this is a model processing equivalence, we used a subset of meta models, so 10 of each environment, because we had to manually test the features so that both platforms behave the same. And because this is a very tedious task, we used a representative subset and tested them manually. And there we could also verify for every meta model that they behave actually the same in either environment. So also this we could show here. So concluding, what we did in this work, we created 2 unidirectional bridges between ADOXX and EMF. And we therefore enabled interoperability between the 2 environments. So we really solved this problem that I described in the beginning. If there's like 2 different teams that want to work together on the same meta model, which was not possible until then, is actually enabled now. And we also offered this transformation procedure publicly on the Institute's website for anyone to upload their meta model and transform it to the other environment. So, and briefly talking about future work, so what we could do from here. So we could look at the model level transformation, because right now in this work we only looked at the meta model level transformation. And with this transformed meta model, we could also transform the models to the target environment. So we could use this work to do that. And we could also transform the concrete syntax. So this is, for example, the graphical representation of the models. So we could look at that, like how can we transform certain styles, for example, if they're in SVG, how can we import them or transform them also to the other environment when we transform the models. And then we could also, as the last thing, maybe analyze a fourth meta model layer above all other layers, because the things we did with the composition and the multiple inheritance, this is really just our way how we defined it. So we could think about moving this even one layer up. So this would be the meta model layer, and we could define the mappings there. So if all other meta models conform to this general M4 model, then we would be able to more easily perform these transformations. So thanks very much for your attention. Other questions?
Thank you very much, Constance. Oscar. Yeah, I was almost already.
Yeah, I know that you have many questions. Okay, thank you very much. It's a great presentation. I like the work very much. It's very complex. I think that is very, very interesting to try to make this connection. But said that, because the most important point is to emphasize in the relevance and the interest and the value. I think that the devil is in the details here. I mean that just trying to connect to meta models with ADOX and EMF is a very complex problem. Yeah. So you are facing different aspects that are really, to me, very complex. So for instance, I was wondering, well, how the evaluation that you did could be a different paper, because, for instance, how to be sure that how are you considering the truth maker perspective? What is true? What is correct? How to evaluate that the validation, the transformation was correct because the right things were happening. Because when you are converting to meta models, of course, the generality, a class is a table in the relational database. This is okay. But there are very, very small details. This is why I said that the devil is in the details that are really hard to be sure that the transformation is fully operational. Yeah. So this is my question, because I think only a simple thing, as you said, as an example of the multiple inheritance, could be a paper by itself. There is many details that are very interesting. So taking into consideration, it's not Klaus here to tell me that I am being too long. But taking into consideration that the problem is very, very important, how to be sure that the solution that you provide is really correct? What about correctness and completeness? Because there are many, many small details that are very, very hard to fix.
Yeah, exactly. So yeah, it is like there's different facets to it.
Before you answer, can I pick back on the question, because to make it a bit harder. So if you go back to the multiple inheritance example and evaluation, one problem is how this impacts in time the translation, right? Because you said I have to replicate the attributes of the superclass here, but it's not the attributes of the superclass. It's all superclasses because of transitivity of inheritance, right? So if you have 30 classes that are inherited here, what happens if all these other hierarchies change? So what is the impact of constraints and all that? So
yes. Do you mean like if they're changed after they're transformed?
Yeah.
Okay, yeah, so of course, like this is a limitation, obviously, so we cannot ensure actually that the user can, so because we do like a lot of transformations and we also add like a lot of different attributes to it as meta information and so on, it is not so trivial, so we kind of, like the user needs to be careful like what he deletes and so on, so this is actually not 100% possible yet, but I mean it could be done, like especially like with the other direction with AutoScript, so we could write extensive code into the other target meta modeling environment to like catch these special cases and like put constraints and limitations on it.
But it's the general point of Oscar's comment, right? That there are these aspects of evaluation that are very important. That it's of course, you cannot do anything after things have been transformed, but you could evaluate what is the impact of transformation choices in the long run, right? If it is very often that people change things in hierarchies and you would have to go back and replicate. But I don't want to steal the question. So Oscar's question was more general about how to be sure that you made a good...
And adapt to what you said, and that is that something that is really interesting from my point of view, and there is also the work of one of my PhD students, David, that is there, is that what I find very interesting, I would like to explore with you all, is to talk about conceptual model assistance or transformation assistance, because maybe the tricky thing of my question is, to me, it's impossible to do it perfect, but it's very useful to provide some kind of computer support to do the transformation. So you have an assistant, a transformer assistant, that following all the rules that you have, that generally speaking are correct, is helping the modeler to do this fine-tuning that should probably have to be done in any case. This is another other aspect that I wanted also to tell you, because could be part of some collaboration in the future.
Oscar, let's behave, the two of us.
Okay, my name is Bert de Brok from the University of Groningen. Yeah. And I was wondering the following, it is more or less related. Is it possible to transform the model of one of the platforms into the other? Because they have a model, you call it meta model or even meta model, but meta models are models as well, and they are modeling platforms, so can they model each other? Can they model, so can you express the meta model of the one as a model in the other? Because they are modeling platforms, and meta models are models.
So the question is, can you write the ADO-XX meta model in eCore and vice versa?
Oh,
exactly.
Yeah, actually, yeah, of course. Yeah, we did this actually, so in the transformation. So this also like the meta model of ADO-XX, the abstract classes that are from the ADO-XX developers, and we also transformed them as well, because we kind of need like those elements, so we do use this information and replicate this, and on that we define the user-defined meta model, which then inherits from this particular classes.
Yeah, and then you also see the difference between them, and what the one is lacking as opposed to the other, for instance. So I think it's a useful exercise so to do.
Thanks.
Further questions? I'm sure Oscar has a second one, but since I have the microphone, so very quick question. How do you decide which classes to maintain as a superclass and which ones to play this deconstruct game?
On the multi-inheritance, so we basically just chose a greedy approach here. So we just chose the first one to, like, of the available classes to inherit from. And I mean, it really doesn't matter like which.
What do you mean the first one? I mean, they're symmetric. Arbitrarily, you mean?
Yeah, arbitrary. So so like in the list of the classes that we get, so we just chose the greedy approach. But in the end, it doesn't matter, because our main objective is to preserve the semantic features and the meaning of the meta model. And with this, it's very generic. So whatever class you take, as long as you copy all the attributes from the other classes and make sure that this is complete, you still have the same effect. So
I see. Thank you very much, Dominic.
If I may add to that, let alone the different patterns that we found for translating multiple inheritance into single inheritance, that would be a whole, a journal paper on its own doing that, and also involving the meta modeler as the user of this, right? So what you mentioned also, Oscar. Yeah, exactly. Thanks, Costa. So we did a pragmatic way because we are not interested in this particular question. And that is also based on our findings, because when maybe you can also show the slide with the selection of the meta models, the four, exactly. So we had a hard time finding actually eCore meta models that have multiple inheritance. We really needed to search for them, because we tried to select all the extreme representations in our data set with the most classes, the least classes, the biggest inheritance level depth, and the smallest, and the most attributes, and the least, right? So this is a very theoretical question, and I would love to collaborate with you, Oscar, to make this a round trip, so we can also track the meta model edits and see, or even suggest some features. That would be very interesting. But that's first step into that direction, I think. Yeah.
Thank you very much. Thank you very much, Costa.
Thanks.